Today, we're doing something really cool. We're going to dissect a utility-scale solar plant, basically treating it like a living, breathing organism. We're diving deep under the hood to really understand its medium voltage, or MV, infrastructure. You know, if you've ever looked at miles of solar panels and wondered, how does all that raw power actually make its way safely to the utility grid? Well, you're in exactly the right place. So let's just jump right in.
All right, here's our roadmap for today. We'll start with the MV infrastructure fundamentals, look at the three-compartment station, trace out the RMU connections and loops, and then check out the MV and LV cable networks. After that, we'll cover earthing and lightning protection and wrap up with SCADA monitoring and control. Let's get to it. Starting off with Section 1, MV infrastructure fundamentals. So, to really get how a power plant ticks, you first have to understand the different leagues, I guess you could say, of electricity it handles. Medium voltage in a PV plant typically operates anywhere from 11 up to 33 kilovolts. And this network has one massive, absolutely vital job. It is the primary power evacuation path. It takes the energy straight from the inverter step-up transformers and acts as this heavy-duty transmission highway, carrying all that power directly out to the utility grid. Now, if we contrast the MV system with the low voltage, or LV system, you'll see two completely different operational worlds. While the MV side is handling that massive 11 to 33 kilovolt transmission to the grid, the LV system is operating much closer to what you'd find in a commercial building, around 400 or 230 volts. The LV system is super important, but it's really playing a supporting role. It's providing auxiliary power for local loads, things like cooling fans, battery chargers, and the SCADA servers. So to put it simply, the MV side is all about minimizing power loss and isolating huge electrical faults using heavy-duty switchgear, while the LV side, that's strictly focused on local safety and keeping the control systems running reliably. Moving right along to Section 2, the three-compartment station. Okay, so the main thing to grasp here is that out in the solar field, the actual power transformation happens inside what we call a three-compartment station. Honestly, the easiest way to think about this is just picturing a transformer station as having three totally distinct but connected rooms. First up, you have the RMU, or ring main unit. This is your compact SF6 gas-insulated switchgear that handles loop switching and transformer protection. Then you have the actual power transformer. This is the heavy lifter. It takes the 0.8 kilovolt output from the inverters and steps it all the way up to 33 kilovolts. And finally, room number 3 is the MDB, the main distribution board, which basically manages the local low-voltage distribution back out to the inverters and those auxiliary services we just talked about. If you trace the AC single-line diagram here, you can visually follow the whole flow of the ecosystem. It's pretty cool, actually. Power starts way down at the bottom from the solar modules, moves into the string inverters, and then gathers at the LV main distribution boards. From there, it flows up into those step-up transformers we just mentioned, and finally pushes out into the MV switchgear network through the RMUs, heading straight for the utility grid interconnection. It's just a beautifully structured hierarchy of power when you really look at it. All right, Section 3, RMU connections and loops. Think about it. If you wire all your stations in a single straight line, one broken cable could literally take your entire power plant offline. No way we're doing that. To prevent a total blackout, the stations are grouped into fail-safe circuits, or loops. For example, the 33 kilovolt feed from the main MV switchgear enters a loop configuration, where loop 01 might tie together transformer stations 1, 2, and 3, meanwhile loop 02 connects stations 4, 5, and 6. Because they're wired in a ring, if one feeder line goes down or needs maintenance, it's no big deal. Power can just be supplied in reverse through the alternate path in the loop. And to actually make those loops possible, the power inside the RMU has to follow a very strict routing sequence. First, it enters via the incoming load brick switch, that's LBS1. Once it hits the RMU bus bar, the power has two options. It can either continue down the line to the next station in the loop through the outgoing load break switch, LBS2, or it can route downwards through a highly protective vacuum circuit breaker, or VCB, going directly into the local power transformer. It's a really elegant traffic control system. Next up, Section 4, MV and LV cable networks. As you might guess, the cables you need for medium voltage versus low voltage are vastly different beasts. MV cables are totally optimized for extreme voltage over long distances.
In standard designs, we're usually talking about 3-core, 120 square millimeter aluminum XLPE cables. And for safety, these are buried a full meter deep in clean sand trenches. But the LV cables connecting the transformer to the MDB, they aren't dealing with high voltage. They're dealing with massively high current. We're talking sometimes over 6,000 amps. So instead of distance, LV connections need massively thick parallel setups, like 4 500 square millimeter copper cables or rigid bus ducts, literally just to carry that load without melting into a puddle. And here is the absolutely critical engineering threshold for those LV cables, 3 to 5%. The voltage drop across these thick LV arteries has to be kept strictly under this limit. If you try to use a cable that's even a little too thin, the resistance causes the voltage to drop, which generates excess heat, and that will severely restrict the amount of power you can actually push into the transformer. It's a make or break metric.
That brings us to Section 5, Earthing and Lightning Protection. So a utility-scale solar plant is essentially a massive, wide-open field filled with metal structures and highly sensitive electronics. Basically, it's prime real estate for a lightning strike. So, how exactly do you protect a 60-megawatt plant from a direct strike that can unleash up to 200,000 amps of pure destructive energy? I mean, without protection, a strike like that would start fires, completely destroy the inverters and SCADA panels, and send lethal overvoltages right through the data cables. The answer is a meticulously engineered, low-impedance path to ground. The entire site is bonded together into this massive main earth loop using copper-bonded steel rods and copper tape, buried right in the earth. The engineering standard here is strict. You have to keep the DC resistance under 3 ohms and the AC resistance across the MV switchgear and RMUs under 5 ohms. Plus, this grounding grid doesn't work alone. It's paired with strategic surge protection devices, or SPDs. Type 1 and Type 2 SPDs are placed at critical junctions, like the string combiner boxes and main LV distribution panels, to instantly shunt any of those lightning transients safely into the dirt before they can fry the equipment.
Which leads us to our final section, Section 6, SCADA, Monitoring and Control. SCADA, which stands for Supervisory Control and Data Acquisition, is basically the central nervous system of the plant. It is constantly reading sensory inputs from everywhere. Using specialized communication cables running RS-485 daisy chains and Modbus protocols, it is pulling in real-time data nonstop. It instantly flags operators if an RMU trips a fault, or say if the SF6 insulating gas pressure drops. It's actively watching the transformers for overheating by monitoring the oil and winding temperature indicators. It tracks literally every power meter and tripped low voltage breaker. It just gives operators total 24/7 situational awareness. Just like a biological nervous system, these control hubs are pulling together millions of data points to keep the plant alive, safe, and perfectly synchronized with the utility grid. If a short circuit happens in the MV network, the protection relay is detected instantly. The circuit breakers trip to isolate the damage, and the SCADA system logs the event, all while allowing the rest of the healthy loops in the plant to just keep pumping power right to the grid.